Over 400 years ago, Galileo turned the first telescope to the stars and forever changed the world. One man's view through his small home-built telescope and the careful notes he left behind removed the Earth from the centre of the universe and redefined our place in the cosmos. Now, two astronomers are on a mission. Using modern telescopes, advanced computing, and some good old-fashioned luck,
That's pretty interesting.
they hope to reproduce one of the most impactful seminal moments in human history and see for themselves what Galileo saw. Right now on Astroveo. As you look to the east on a clear winter evening, you'll likely notice a bright star hovering far above the horizon. That is no star at all, but the gas giant Jupiter, the largest planet in the solar system. It is home to the famous giant red spot, a massive hurricane larger than the entire planet Earth. Jupiter is a dynamic world, showing a new face with each observation. Jupiter is orbited by a system of almost 100 moons, the four largest of which can be easily seen even through small binoculars. Like their host giant, these moons are each complex and rich worlds. Io, sulfur-coloured and similar in size to our own moon, is covered with volcanoes, allowing us to obtain the first images and videos of extraterrestrial volcanic activity. Amalthea, one of Jupiter's smallest moons, is the reddest known object in the solar system. And hidden beneath the impossibly smooth surface of Europa is a subsurface ocean, hypothesized to be our best chance of finding extraterrestrial or alien life in our own solar system. It was Europa, along with Ganymede, Callisto and Io, that Galileo would observe when he turned the first telescope to the stars in 1610. Galileo did not invent the telescope. The so-called Danish perspective glass had been patented the year before, but Galileo quickly improved upon the design and was the first to use his telescope to carefully observe the night sky. The ability to magnify images beyond the power of the human eye opened up the entire universe to the collective gaze of humanity, and thus, in Galileo's backyard, astronomy as we know it was born. Galileo's observations of the moon and stars alone redefined our place in the cosmos, but his careful observations of Jupiter shook science, religion, and human understanding to the very core. On the 7th of January 1610, Galileo pointed his small telescope at the planet Jupiter and sketched a sight that had become common for him: the presence of three new, smaller stars, only made visible by his telescope. These stars were arranged in a perfect line around Jupiter, which Galileo took to be a curious coincidence. The next night, when he spontaneously decided to observe Jupiter once more, he was astonished to discover that while the three stars around Jupiter were still there, they had apparently moved. Intrigued, he began carefully recording the position of Jupiter's companion stars every night. As he watched, the three stars continued their periodic dance near Jupiter, vanishing when they touched the planet's right side and reappearing several hours later on the left. A week later, after a fourth star appeared and began matching the motion of the other three, Galileo came to a stunning conclusion, a conclusion that would challenge every accepted prior notion about the universe. The stars were not in fact stars, but moons like our very own. And they were in fact orbiting Jupiter, not vanishing at all, but passing behind the much larger planet and out of view. In one observation, on a single night, our view of the cosmos shifted. While it was previously thought that everything in the universe orbited the Earth, Galileo identified the first conclusive evidence of a system that did not. The Earth was no longer a unique central point in the majesty of an intelligent creation, but instead a random one of an infinite number of copies of the same basic system. In his observations of a system of moving particles bound by an attractive force to a massive central object, he unknowingly stumbled upon the fundamental principle underpinning the mechanics of the entire universe. From galaxies swirling into black holes, to the dance of stars on their planets, all the way down to the smallest atoms and the orbits of electrons around their nuclei. Santa Barbara, Pacific West Coast, California. The Las Cumbres Observatory. Long after the workday is done, we stay behind, intent on solving a single mystery. What exactly did Galileo see just over 400 years ago? Over several nights, Galileo recorded the details of his observations of the Jovian system. Hidden in his careful notes and diagrams are clues to the phase of the orbital cycle Galileo observed at the beginning of the 17th century. Right now, Jupiter's moons are still orbiting the planet in a beautiful gravitational dance, following the same periodic cycle that Galileo witnessed. Which means, every so often, Jupiter once again shows us what it showed Galileo. Using modern simulations of the orbital mechanics of Jupiter and its moons, we can make precise predictions of where those moons will be on every night in the future.
So kind of the goal here is we have these excellent notes from Galileo where he sort of showed the position of the moons of Jupiter as he saw them on each night of his observations, sometimes multiple times. And what we want to be able to do is match that up with these excellent simulations we can create of this Jovian system.
The problem is, it is quite tedious for a human to stay up all night, in the cold, to check the positions of the moons, second by second, in order to compare to Galileo's notes. Fortunately, this is an easy task for a modern computer to do. But a computer cannot simply look at Galileo's notes in the same way a human can. The next step, then, is to figure out how we can convert Galileo's precise drawings into something a computer can easily read and interpret.
Okay, so right now we've got this script that will allow us to take Galileo's notes and convert them into a format that the simulation can read. So the simulation is able to understand the position of the moons, etc. around Jupiter, and then convert that into a distance from Jupiter, which is basically what Galileo is seeing. We can see that this image is black pixels marking out the moon and Jupiter on a roughly white background. And what we can do is we can convert this image into black and white and invert it. If we pass through this image and add up all the pixel values in each column, the spikes will tell us where Jupiter and the moons are. We can easily extract the positions of the moons and convert them into a format that the simulation can understand.
With just a little bit of Python script, we can now ask the computer to interpret Galileo's notes and feed the output into the simulation, which will then check billions of future moon configurations for potential matches. We can sort matches by similarity and see if there is a match coming up soon.
So I've run the simulation of all the nights of data that Galileo gathered on Jupiter, and it's identified this night from a couple days into his observations as actually occurring tonight. So that's really exciting. So we're going to go out and try and see if we can capture this moment from Galileo's observations.
A Jovian event coming up tonight means there's no time to lose. Planetary astrophotography is quite challenging and risky, with many failure points that can compromise a night of observation. In order to make the observations we're striving for tonight, we'll need access to specialized equipment and more. But do you really need all of this just to see the moons of Jupiter yourself?
A lot of people think that you need a telescope or something in order to do visual astronomy, but you can actually get quite a bit done with just a pair of good binoculars. You can see stuff like the moons of Jupiter, even planets like Uranus and Neptune, and the odd comet, which is a good pair of binoculars. In fact, the telescope that Galileo had when he made his big discoveries about the moons of Jupiter wasn't that much better in magnification than the binoculars I have right here. And because of this, he wasn't able to see the moons as anything other than bright stars, and the face of Jupiter was just a flat disk, completely white. But we have slightly better telescopes, bigger and better than what Galileo had access to. And so with any luck, with our observation tonight, we'll be able to not just see the moons and Jupiter, but actually surface details on Jupiter itself, like the great red spot rotating around. And if we're even lucky, if we're really lucky, we might be able to see surface details on the moons themselves.
The primary difficulty in observing the planets of our solar system is in resolving their tiny size on the sky. Planets are very, very far away, and as a result appear extremely small. So in order to capture them in stunning detail, we need to use large telescopes, very large. How large, you say?
Oh, that barely cleared it. Oh my lord. Oh, that's uncomfortable. Oh, it's pointing at me. I'll point it at you. Ah! Thing is so big.
Okay, not quite that large, but the same principles do apply.
So, planetary astrophotography, you need a special kind of equipment set in order to do it. It's a different beast from regular astronomy. You see, planets are really small, and you need really good resolution in order to make them big and see them in their full magnificence. That's why you need big telescopes like this. You see, the bigger a telescope's mirror is, the better angular resolution it has, which means the smaller thing it can see on the sky. And so in order to make planets big enough to see their fine details, you need as big a mirror as possible, basically. So the problem is, though, because planets are so small, they're really susceptible to this thing called atmospheric turbulence. And we measure atmospheric turbulence with a condition called seeing. So if the seeing is good on a particular night, it means that the atmosphere was quite calm. And so the image is not very disturbed by the air in the atmosphere, and so you can just take a picture and it'll probably look pretty good. But if the seeing is bad, which happens to me very often, that means the atmosphere is very turbulent, and as a result, you're going to need to do a process called lucky imaging in order to make the best image you can. Lucky imaging basically involves taking many frames of an object and then throwing out the bad ones where the atmosphere is very turbulent and just keeping those few precious seconds where the atmosphere was calm and making an image out of those.
We'll be using some special hardware to capture Jupiter and its moons during this rare event. To start, we'll be using a Celestron NexStar 6SE, a powerful 6-inch Schmidt-Cassegrain telescope with built-in go-to tracking and crystal clear optics. The large aperture will help us resolve surface details on Jupiter, and the sidereal tracking will help ensure that we have high-quality, stable data. This modern, mirror-based telescope will be able to magnify Jupiter almost 20 times more than Galileo's hand-built, lens-based masterpiece. The view from the telescope will be fed into a ZWO ASI 224MC, a special dedicated planetary astrophotography camera. The small but dense CCD, a charged couple device, which is an imaging detector similar to the CMOS detector in most mobile telephones, combined with USB 3 connectivity, will allow us to perform lucky imaging and get the best image possible, even with less than ideal seeing conditions. We'll be capturing the data from the ZWO using the Fire Capture program, which has special functionality to make observations like this straightforward. With all of the equipment ready to go, and the time of the event predicted down to the second, the only thing left to do is to wait for the sun to set and for Jupiter to rise. As Jupiter comes into view, we aim our telescope at the distant planet. We've set up a dew shield on the end of the telescope to keep the optics dry, and we are repurposing a green screen to keep the telescope steady during any winds that might crop up. We first align the telescope with Jupiter and enable the tracking to keep the planet centered in the field of view. If you look carefully, you can see the telescope sidereally tracking, slowly correcting its position to keep Jupiter in view as the night goes on. Once Jupiter is centered and tracking, we calibrate the focus and camera settings to avoid under and overexposing the planet. Seeing Jupiter pop into view never gets old. The banding in Jupiter's atmosphere, due to its rapid rotation of only 10 hours about its axis, is immediately visible, even in the live view. We've begun recording now. The camera is saving exposures to a large-scale storage medium at over 200 frames per second, which means in our few minutes per exposure, we'll be able to capture 30 to 40,000 frames, ideal for lucky imaging. It's only a few minutes, but each exposure requires several gigabytes of storage space to save. We'll repeat this process every 10 minutes or so for a few hours, which will let us make a time-lapse of Jupiter and the Galilean moons, and see if we are able to reproduce Galileo's fateful discovery. It was a successful run. Yay! With the weather holding still for several hours, we were able to collect 12 frames of the evolution of Jupiter and its moons. Back at the Las Cumbres Observatory, we can process the data using specialized astrophotography software designed specifically for lucky imaging.
So in order to process the planet Jupiter, the process is pretty simple. We're going to use a software called AstroSurface. So we're just going to go and open up one of the files. I'm picking the 9th frame of the data I took tonight. We'll blow this up, make it bigger so we can see it, and you can see if we scrub through the timeline, we can see the different images as the telescope saw it. So we're going to click on Analyze and Register, and what this is going to do is it's going to detect the location of the planet and attempt to analyze each of the frames and sort them based on quality. This is the lucky imaging process that we were talking about earlier. We're going to set these things called alignment points that will allow us to align the image in each frame so that we can stack and average the pixels. And now when we perform the stack, we see we get an image out of it. We're going to blow up this image, and right now it doesn't look very good. You can actually already see the great red spot and the bands, but not that much. So we're going to resize this image by a factor of 3, and we're going to rotate it, and now we're going to apply a wavelet setting, which you'll immediately see that this deconvolution procedure brings out a lot of the detail. You can see the great red spot, you can see the banding really well, and finally we're just going to apply a quick white balance correction to make the planet look a little bit more like what it looks like in real life. It's like to match what I saw when I looked through the eyepiece.
With 12 processed frames in hand, we align and center them to produce the final movie. The rotation of the surface of the planet is immediately clear. Just beginning to appear at the very start of our observation, Jupiter's famous Great Red Spot drifts across the image as the planet rotates. It is important to remember that while the Great Red Spot may look small on Jupiter, this massive storm is much larger than the entire planet Earth. We can use our observations of this storm to calculate important information about Jupiter and provide physical constraints about its atmosphere.
Thanks to the visibility of the Great Red Spot, we can do a bit of science with our images and try to estimate the rotation period of Jupiter. Jupiter rotates at a constant rate. If we measure the position angle of the Great Red Spot at 2 different times, we can estimate an angular velocity and use it to calculate how long it would take the Great Red Spot to complete one full pass around the planet. This quantity is an estimate of the period of Jupiter. The first frame of our observation shows the Great Red Spot at about a 45-degree angle measured from the left. This observation was conducted at about 8:07 p.m. on the night of the observation. 5 frames later, the Great Red Spot is face on at about a 90-degree angle. This observation was taken at 9:24 p.m. This indicates that the Great Red Spot traveled about 45 degrees in about 77 minutes. A full orbit is 360 degrees, So this implies that the rotation period of Jupiter is about 616 minutes, or just over 10 hours. If we compare this to a NASA measurement, we find they recorded a rotation period of 9.9 hours, which is confirmed by our observation. It's pretty cool to think that you can confirm a NASA statistic from your backyard.
Beyond the Great Red Spot, Jupiter's surface comes alive in our images, in swirling hues of orange, white, and brown. With just our 6-inch aperture telescope, we are able to resolve individual cloud bands in Jupiter's atmosphere and take notes of their remarkable features. Jupiter's distinct colours come from its rich and complex chemical composition. While Jupiter is primarily composed of hydrogen and helium, the presence of ammonium hydrosulfide, sulfur, phosphorus, and water ice in the upper atmosphere produces a dazzling mixture of colours. The rapid rotation period we estimated earlier, at just over 10 hours, creates powerful jet streams across the entire planet, stratifying its clouds into these unmistakable bands. Besides the Great Red Spot, we can clearly make out multiple smaller storm cells, similar to Earth's Hadley cells, as they rotate across Jupiter's surface. Even at our resolution, we can confirm the observation of NASA and other astronomers, and including the presence of this spoon-like storm that has been slowly encircling the Great Red Spot since 2015. In fact, Jupiter's entire surface is one gigantic fluid experiment on a massive planetary scale, playing out in real time right before our eyes. Zooming out far beyond Jupiter's surface, at about 250,000 miles to be more precise, we find 3 more celestial bodies, far, far smaller than Jupiter itself. These are, of course, 3 of the 4 Galilean moons we have worked hard to image. From left to right, these moons are Europa, Io, and Ganymede. Although there is no obvious surface detail present, it is nevertheless remarkable that we have captured images at all of objects the size of our own moon at almost 500 million miles away. And through our careful time-lapse, we can see all 3 moons as they proceed in their orbits around their host gas giant planet. By inverting the colour scheme, we can make our own version of Galileo's notes and compare them to our predicted event to see if they line up. As one can see, the position of the moons relative to Jupiter appear to be extremely similar to what Galileo observed. The end result of our efforts, through historical examination, computer simulations, and modern observing techniques, is this. By standing on the shoulders of giants, with this stunning single comparison, we have succeeded in our quest to see for ourselves what Galileo saw.
You just love our astronomy nights, don't you? Don't you, buddy? Don't you? Hi, pal. How you doing? Oh, that's right. That's right, buddy. That's right. Say hello, Astro Puppy. Say hello. Say hello. Oh, thank you for the kiss.